Alright, so the next example, we're going to write a Taylor polynomial. So Taylor just means that we are not centered at 0. So in this case, we are going to have a degree 6. So we need up to the 6th derivative. We're using f of x equals natural log of x, and this time we will be centered at 1. After we've done all of that, then we can use it to answer the question to write that approximation. So let's start by finding the first 6 derivatives. So we have f of x, which is equal to the natural log of x, f prime of x, which is equal to 1 over x, f double prime of x, which is equal to, so technically we're just rewriting this as x to the negative 1, and then using the power rule, so I've got negative 1 over x squared, f triple prime of x, which is going to be equal to a positive 2 over x cubed. Then I have the fourth derivative of x, which is going to be equal to a negative 6 over x to the fourth. I've got the fifth derivative of x, which is going to be equal to a 24 over x to the fifth. Then we have the sixth derivative of x, which is going to be equal to a negative 120 over x to the sixth. Now I also want to go ahead and evaluate each of those at the center. So this time we're going to evaluate at 1 instead of 0. So f of 1, which is equal to 0. F prime of 1, which is going to be equal to 1. F double prime of 1 is negative 1. F triple prime of 1 is going to be 2. The fourth derivative evaluated at 1 is going to give me a negative 6. The fifth derivative evaluated at 1 is going to give me 24. And then the sixth derivative evaluated at 1 is going to give me a negative 120. Excuse me. Alright, so now let's plug that into our definition. So we've got P6 of x is going to be equal to, so the first one's just going to be f of c. So f of c is equal to 0, plus, now we're going to go through with the first derivative. So first derivative is 1 times, remember it's x minus c, so x minus 1 to the first over 1 factorial. Now the second derivative, so second derivative is negative 1, x minus 1 squared over 2 factorial, plus the third derivative, which was 2, so 2 times x minus 1 to the third over 3 factorial, plus the fourth derivative was negative 6 times x minus 1 to the fourth over 4 factorial. Then the fifth derivative was 24 times x minus 1 to the fifth over 5 factorial, plus our sixth derivative, which was negative 120 times x minus 1 to the sixth over 6 factorial. Excuse me. Alright, so we could do a little bit of simplifying here. Not super necessary, but just for the sake of looking at how these factorials can cancel. I know that 0 goes away, 1 factorial is just 1, so this first term is really just x minus 1. Right? Second term, 2 factorial is just 2, so what I really have here is minus x minus 1 squared over 2, plus, now 3 factorial. 3 factorial is 3 times 2 times 1, so the 2 actually gets rid of the 2 times 1, and what we're left with is x minus 1 cubed over 3 minus, now here, so 4 factorial is really 4 times 3 times 2 times 1, where the 3 times 2 times 1 is just the 6. So the 6 will cancel, and it just leaves me with 4 on bottom. Then I have plus. Now the same thing happens here. 5 factorial is 5 times 24. So the 24 is going to cancel. I've got x minus 1 to the 5th over 5. And then the same thing is going to happen on the last one. Minus x minus 1 to the 6th over 6. Right? So some things that you may want to take the time to learn. So what we know is that 0 factorial is equal to 1. 1 factorial is equal to 1. So the idea behind 0 factorial equaling 1, if you Google it, you can find videos where people are explaining that. So 2 factorial is equal to 2. 3 factorial is equal to 6. 4 factorial is equal to 24. 5 factorial is equal to 120. 6 factorial is equal to 720. So if you know those offhand, it makes simplifying these Taylor polynomials a little easier. Now the last thing it asked us to do was to evaluate. So we're going to come back up here and we're actually going to evaluate our polynomial at 1.1. So we're using our calculator. Well, that should be an evaluation symbol or approximately symbol. So we've got P6 of 1.1 is approximately, and so we're going to use our calculator to plug that in because we don't want to have to sit here and do all that math. But the idea is that this is, having a polynomial is something that I could plug 1.1 into. In this case, I'm going to get 0.0953. I just went an extra decimal place there because we had the 0 in that original place. Alright, so one more example for today. So example 4, so they've set it up a little differently. And so we really just need to, you have to really know and understand the definition of a Taylor polynomial here. Alright, so what I'm going to do is I'm going to write out the information they gave us. So I've got g of 2 is equal to 3. And I'm going to write it in the same column format that I was writing it in the other examples. Because then it's just, if you are always organizing your information the same way, then it makes it a little easier to remember how to put it into the definition itself. Now, it's asking us to write a Taylor polynomial of degree 3. Notice they gave us 3 derivatives. So this should be, that's just a typo. So I've got a negative 5. This is just negative 5. And then it's asking us to center it at 2. So notice that we've evaluated all of our derivatives at 2. So now what I need to do is plug into the definition. So I'm going to write out the formal definition here without the 2 and without our derivative values. And so the third degree polynomial here using g of x would be g of x plus g prime of x, x minus c to the first over 1 factorial, plus g double prime of x times x minus c squared over 2 factorial, plus g triple prime of x times x minus c to the third over 3 factorial. So now let's plug in what we know. So I've got P3 of x is equal to, so g of 2 was 3, plus g prime of 2 was a negative 4, x minus 2 to the first over 1 factorial, plus g double prime was 7, x minus 2 squared over 2 factorial, plus g triple prime of 2 was a negative 5 times x minus 2 cubed over 3 factorial. It didn't ask us to approximate anything here. It was just asking us to write the polynomial. So this would be our answer.